So let's look a little bit more closely at what a neutron star is. We said now we know there's two types of supernova explosions, and a neutron star is one of two possibilities after what we call a supernova type 2 explosion, where a massive star ends its life. You might get a neutron star. So the deal with a neutron star is that the electron degeneracy that holds up a white dwarf, the way I think of it is the electron degeneracy fails. And so under the weight, basically the density that's being drawn in on that object in a neutron star, the electrons combined with protons and go to form neutrons. So there's like a transformation of subatomic particles here, which I just find amazing. And so what a neutron star is, it's kind of exotic compared to our regular atoms here on Earth. And a neutron star is what I kind of call a ball of neutron soup out there. So a neutron star then is basically, I tell students, if you have a big family gathering at Christmas time and you have all sorts of kids that are unwrapping their presents, and if you're like me, sometimes the whole unwrapping process can go on for hours, it seems like. But if you're in charge of gathering the used wrapping paper into one plastic bag, so what happens is you kind of just say, for whatever dumb reason, you only have one plastic trash bag. And so you put the wrapping paper in there and you stomp it down. And you're like, oh, I got more wrapping paper. You put more wrapping paper in there, you stomp it down. You put more wrapping paper in there, you stomp it down. At some point you have a white dwarf, right? Well, let's just say what a neutron star is, you stomp it down even more. And so it's really compressed material. So in general, for instance, for a neutron star that has about one, I think this is right, about, I don't know, one solar mass, or maybe 3 solar masses. I guess I should say between 1.5 and 3 solar masses in general. This neutron star would be squashed down to about the size of Lansing. So neutron stars, the discovery is kind of a fun story. So when radio astronomy was kind of new, remember that we can look at objects in the radio, these long wavelengths, and we can understand things about those celestial objects. Well, they scanned the nighttime sky or the daytime sky. You can do radio astronomy during the day too. But they scanned the sky and they came up with this sort of pulsing radio signal. And at first, and I think I got this right, at first they were thinking that sort of radio signal, very regular pulses, that maybe it was coming from intelligent life. And so these signals were temporarily called LGM, standing for Little Green Men signals. I just think that's so fun. I just think astrophysicists must be the funnest people on Earth. But anyway, as it turns out, these radio signals, these very regular pulses, they were being created by a neutron star. Now the signal themselves we call a pulsar, but the pulsar is created from a spinning neutron star. Okay, so this is the Supernova Remnant. This is where a supernova type 2 event, and basically you can see its guts. Isn't that beautiful? Were spewed out. And in the middle of that supernova remnant is the core of the star that was once alive, and it is a neutron star. And so I think that these might even be in the visible region of the electromagnetic spectrum. Can you see where that neutron star is kind of blinking? But if you look at the numbers there, the frequency is like 0.033 seconds. I guess I should say that the time between blips is 0.033 seconds. Is that crazy or what? That's very fast. So I'm going to go ahead and play you this. This is that pulsar. Remember, pulsars are kind of the blipping that's coming from a neutron star. So the Chandra telescope is a NASA project. There's no sound with this. But from left to right, you're looking at 2 different wavelengths. And it just reminds me, if you've ever seen an image of a fetus, that's kind of what that looks like to me. Isn't that cool? 2 different wavelengths. So there's a neutron star down there sending us those ongoing pulses. So how does a neutron star give us pulsars, a phenomenon we call pulsars? Well, it kind of goes back to, do you remember we talked about that planets like the Earth can have what we call a magnetosphere if they have some sort of ooey-gooeyness to their core, if they have some sort of liquid charges that can spin around as the planet rotates? Well, so picture this neutron star that actually is kind of a flow, very fluid, and we have charged particles, made up of charged particles, and so as it spins, it can create a magnetosphere. One of the things about the magnetospheres or magnetic field of a planet is that it doesn't have to coincide with its axis of rotation. So for instance, you kind of see the white stick here is the pole that the neutron star is spinning on, and you can see that its magnetic field actually is kind of tipped over. Oh, in this case, it looks like it's maybe about 45 degrees. And then what happens is kind of out the center where these would be the magnetic poles, actually there are beams of energy that are going both directions. So as this neutron star spins on its axis, that beam of light swings around, okay? And if we are in the path of it swinging around, then we see it blip on and off, on and off, on and off. Sometimes this is called, we kind of have a situation with if you're familiar with a lighthouse basically has a light that goes around and around and around and around. And that's kind of what we have with pulsars from our perspective. So you're like, all right, so why do we think that beam of light that we call a pulsar, or beam of energy, maybe it's radio waves, is a pulsar? Why do we think that its actually source is a neutron star? Well, we can understand certain aspects of the object that's creating the pulsar. And for instance, it's very small, it's very dense, and it's rotating very, very quickly. And just regular matter as we know it couldn't survive that. So kind of we're deducing that it is a neutron star. Anything else in normal matter would be torn to pieces. But that neutron soup object works just fine. One more slide. So neutron stars spin very quickly, and it kind of goes back to the fact that you have taken a very large object, i.e. a star, that was one point spinning on its axis, and you have squished it down. So the more you squish it down, the faster it goes. And so all that conservation of angular momentum makes for a very fast-moving neutron star.